Yes, welcome to our inaugural webinar series for FIT and our um, offerings for current and existing and future customers. So what I'm going to go over today is general, when I talk about sockets. A socket normally in the past and in what everybody's used to are sockets when you think of the CPUs for Intel and AMD, but sockets over the past decade have become more versatile to go beyond just for CPU processors to expand upon that. And so what I'm going to touch upon is, in general, when we talk socket, we're talking about a generic terminology for socket, where a socket could be, again, for a processor, it could be any ASICs device, as well as any interconnectivity between two mating surfaces which exist, LGA pads. Okay, so it's kind of going beyond that. So currently in the industry that uses sockets, what you most commonly see, which is in the highest volumes, are in the CPU and memory. So you're talking about your processors and your DDR. That's the current mass volume that you see. But we also have seen over the past decade an increased interest in switch ASICs, such as your Broadcoms, but also optical engines as we move forward to another industry growth in the CPO and CPX. Okay. The even more recent is a transition away from your direct attach of GPUs, APUs to socketing your GPUs. And then the other one that's been out there for a number of decades, for more than 20 or 30 years, are your sockets are used for your burn-in testing and your test sockets using pogo pins. Okay. So similar challenges across the industry. Obviously, we're going higher speeds. That's the trend, and it continues to do that. SI performance is up to 56 gigahertz, and we do see it going well beyond that as you go into beyond PCI Gen 6 to the undetermined PCI Gen 7, etc., above 56 gigahertz. For impedance, right now, again, the current trend is about 92 to 100 ohms. Differentials for Ethernet, and then in the PCIe DDR, 85 ohms differential. Okay. Power, everything's becoming more power hungry. So we are seeing an increase in power demand where things are going. The current is about, current ratings we see is anywhere from 1 to 2 amps, but now we're seeing a growth beyond 2.5 amps per contact, or say per pad, if you will, or per pin, with some industry customers looking at a power per millimeter square above 4 amps. And the last item here is high density. So everybody wants things to get more pins and a smaller footprint. Again, we have the capability of doing a 0.4 millimeter pitch in about the 500 pin range, but there again become limitations in the system stack itself when it comes to smaller pitches. Let's take a look at trends. So in this slide here, this is the I would say the LGA pad or ball to ball pitch in mass production. Again, this shows the average pitch. And when I talk about this, I'm talking about whether the pitch is in a hex pattern, which is actually an example on the right-hand side, or orthogonal, where it's just a true XY. If we look at a BGA to LGA, and that's your typical CPU sockets like for Intel and AMD, where there's a solder ball that reflows to the PCB, and then the LGA tip wipes across the LGA pad. Since 2020, we saw the pitch above 1 millimeter, but you can see as the trend goes over the past 25 years, past 5 years, not 25, after the past 5 years, there's been a big trend to try to get that pitch down even lower. Right now, the most common pitch is around the 0.9 millimeter in mass production, but we're seeing that trend go even further. The other blue line is the LGA to LGA. This is a dual compression. An example of one is on the right-hand side. This is where there is no surface mount solder ball reflow, where the socket or interposer has a compression beam on the top and the bottom side. That's been holding pretty steady across the years, where it's in the, right around the zero 0.8 to 0.85 trend. But again, we're seeing those two lines converge in a similar. But again, we have the capability going below 0.8. Okay. Socket height. This trend, what we talk about here is socket height. The socket height is the distance between the PCB and the package. That would be, in other words, like the signal, the Z direction signal length. The signal height average, again, in mass production for your BGA to LGA sockets for CPUs, etc., has been pretty slowly trending downwards, but hasn't gone much below the 2 millimeter. There is some demand to go below 2 millimeter, but because of the nature of the design, there are limitations due to the stack of the contact and the solder ball that are used in those traditional sockets. Dual compression LGA to LGA, because those are much shorter contacts and there's no solder ball involved, you can actually get those down. So right now in mass production, it's in about the 1 millimeter range, but we're seeing an interest to go shorter. And that interest has grown because the shorter that distance becomes between the package and the PCB, the less signal path, signal length that occurs. So that smaller that gap, the shorter the signal path has to go. The last slide here is talking about pin counts. So this is basically the number of pins or contacts within a socket. Dual compression sockets allow us to go to higher pin counts because of the lack of SMT reflow temperatures needed. Currently, today, we make over 8,000 pins mass production for a dual compression LGA to LGA, but we've actually made sockets in the 13,000 range as well. If we look at your traditional LGA to BGA sockets for like Intel and AMD, that trend has been slowly growing. As of today, we're in about the 6,000 to 7,000 pin, but I'm seeing a trend to go above 7,000 pins to 8 or even higher. But again, it comes with its own set of challenges because of SMT temperatures affecting plastic warpage. So I talked about earlier that sockets no longer just mainly used as a general term for CPUs like Intel and AMD. We're seeing an interest in sockets, if you will, or interposers to replace mezzanine connectors. So there are differences between the two. So from a mechanical standpoint, the sockets, if you will, or interposer allows the customer to define their own array without concerns about any standardization of the layout, whereas mezzanines have dedicated ground blades. Density. Higher density for SI, again, we don't really have a limitation on the density. On our side, like I said, we have the capability going down to 0.4 millimeter pitch, whereas sometimes mezzanines do have some limitations. Array sizes, as I mentioned before, we've proven that we can make arrays up to 14,000 positions. Compressive hardware, so because you're talking about these compressive contacts, dual compression or single compression, you do have to compress the contacts, whereas mezzanines don't necessarily need that just because they're more of a plug-in receptacle. Ease of demating, dual compression LGA to LGA sockets essentially just disconnect very easily. There's no damage to the board. They have just some simple alignment holes, whereas the mezzanine typically requires higher removal forces and a little bit more difficult. Mechanical alignment, interposers just use a couple of plastic guide pins to align to the PCB, so it's rather simplistic. With the mezzanine connectors, typically have challenges with blind mating and sometimes multiple mated pairs. Mechanical robustness, these contacts are rather small. And if anybody has experience with sockets, that they do require some special care and handling during installation and removal because of those contacts being such a thin material. Contact mechanical wipe, the sockets have higher Z tolerance stack up, so we actually control very well on the tolerances. Diverse contact array proven. So again, we see no limitations on our end, whether it's a hex or orthogonal, or even in some cases, if somebody wants to do a contact anywhere where there is no pattern whatsoever and it's completely random. Okay. Tolerance analysis complexity. So with these contacts, obviously we have to hold very, very tight tolerances to ensure that we have good deflection and good wipe. But again, with our several decades of experience, FIT has no concerns and no issues controlling very tight tolerances. Okay. Stack height electrical path, as described previously in the socket height. Again, the contact compression height between the PCB and the package, or two PCBs, can be less than 2 millimeters. The mezzanines, because of their construction, they typically require anywhere from 5 to 11 millimeters. So that also becomes sometimes a constraint and concern for customers when they want to have a lot of these thinner blade systems, right? Space is always a concern when you want to have more systems in a smaller footprint within a rack. SI performance, we make directly to a chip. When we talk about this, so whether it's a chip to board interface or board to board, it's a direct interface. Mezzanines typically require a PCB interface between the chip and the mezzanine. So in some instances, the customer's, let's say, GPU chip attaches to a PCB, and then that PCB attaches to a mezzanine to then another PCB. Less discontinuities. We have two mating interfaces. You've got one tip touching one side of the pack. You basically got the top tip of the contact and the bottom tap, the bottom part of the tip contacting it. With mezzanine, there are three mating interfaces. Okay. All right, so sockets and hardware. So again, if anybody's familiar with FIT, formerly, Foxconn, we've been making sockets for quite a long time. So if we just look at the server market, to date, just looking at server, not looking at desktop or any others, just Intel and AMD alone, we've produced well over 30 plus million sockets. And that's going to continue to grow over the several decades. In addition to that, we've also designed well over 30 plus custom sockets for different customers, such as like ASICs, like Broadcom. And to date, as we continue, we're the number one in socket sketch to scale, both in intellectual property, FEA analysis, DFM, manufacturing capacity for mass production, and also it's a signal integrity. So as an example, FIT is a total solution provider. So we do everything internal, vertically integrated. So all components are produced within FIT. The heat sinks are designed and developed by one of our sister partners at Foxconn. This picture on the right is one of the Intel Purley Whitley programs. So all of the components, excluding the heatsink, are manufactured by FIT internally. Okay. But again, we do this for all of our customers if they so choose, where we can either build to print if it's specified by the customer, or we do the entire design ourselves and provide the best solution for the application. Advanced array manufacturing. FIT is the leading industry manufacturer when it comes to mass production. We have, just as an example, when we do contact insertion or insertion of contacts, we do well over 150 contacts per second in mass production. And we can do multiple sockets within the same production line. So we have advanced stamping and contact insertion automation know-how with well over several decades of Intel and AMD socket design and automation experience. As far as limitations, to date in production, we're doing a 13,700 array socket. Again, there's no ceiling to it at this point because nobody has approached that ceiling for us. We have increased confidence in the plastic and injection molding than our leading competitors. Industry leading pitch, shrinking pitch beyond the traditional socket. Again, like I said, the common trend right now is about the 0.9 range, but over the past decades, we have proven that we can produce sockets in the 0.4 millimeter pitch. Okay. FIT offers industry-leading connector analysis. Purpose-built silicon teams can utilize FIT's strengths and legacy in socket development. So we have multiple teams with high degrees to run our contact mechanical FEA analyses. We also have an advanced molding department team, which gives us the predictions and improvements when it comes to warpage, both initial and the dynamic warpage. And the dynamic warpage is the change in the shape of the socket when it goes to reflow temperatures, and also structure integrity of the housing. So we do a lot of advanced engineering prior to even tooling up components. SI analysis, as the industry becomes more focused on signal integrity, FIT continues to grow and have leading engineers who do advanced SI simulations for both differential and single-ended pairs up into the higher frequencies that we're looking at well beyond 56 gigahertz and beyond the PCIe Gen 6, Gen 7. But also we do a model to measurement correlation where we will take those SI simulations and compare them and correlate them with actual SI testing at FIT. So we have full SI testing capabilities to do a correlation with the SI simulation modeling. And finally, reliability testing. FIT has a full array of reliability testing that allows us to test all of the IPC, JDEC, ASTM, and Asian reliability tests out there. So we have full capability to do all reliability testing, as well as detailed analysis from grain structure analysis, cross-sectioning, material analysis for SEM, EDS. Okay. Custom retention mechanisms. Again, when we talk about this, these are basically this is the loading hardware that allows the device or PCB to have compression with the socket. So for quite a bit of decades, we have done a lot of custom retention mechanisms, whether it's a customized for a particular customer, or if a customer has a reference design from like Intel or AMD, but they want something customized to suit their needs, we will do that for them. Okay. What I'll talk about here in the next slides are sockets benefits versus direct attach. Again, the direct attach is what you see out there when the IC will be directly reflowed to a PCB. What is a socket? If you don't know what a socket is, a socket consists of 4 key components. You've got the injection molded LCP body of the socket, which the chip will go into and align to alignment walls within the socket. So it'll sit inside of a pocket. You've got a pick and place cap, which protects the contacts during handling prior to the chip being inserted. So the pick and place cap stay attached to the socket during reflow and protects the contacts. And then right before the chip is placed inside the socket, that protective cover is removed. Then there is the core brains of the socket, which is the contact. In this image here, I'm just showing an example of the AMD SP3, which is used for the Rome and Milan processor family. So they have key features which allow us to do stamping and forming, but also insertion into the housing. And then for SMT sockets, you have solder balls, which allow us to reflow the socket and attach it to a PCB. Okay. Benefits of socketing IC devices. So when I say IC devices, it's any chip, whether it's a CPU, APU, or some sort of ASICs Ethernet switch chip. The nice thing about socketing a device is, or socketing anything, if you will, customers can upgrade the processor in this particular instance instead of the entire system every few years. So oftentimes, customers such as AMD, we will design a socket which is multi-generation. So for AMD's SP3 and SP5 sockets, they accept several generations of CPUs over the year. So for SP3, it's compatible with Rome and Milan, and for the SP5, it's compatible with Genoa and the follow-on Bergamo CPU. So it allows you to reuse the same socket and just upgrade your system without having to replace the socket. Sockets are for more than just CPUs. Like I had mentioned earlier, is that, and this is public information, if you go out there, you know that AMD has announced their MI300 CPU GPU, or their APU. And these are images, you can find this on the internet. So FIT, it has developed and designed a socket solution for AMD's MI300, leveraging the SP5 socket platform. So in that instance, they made some slight changes to the loading hardware in order to utilize a similar design for their APU MI300. And that's the trend that we're seeing, is getting away from direct attach GPUs, if you will, or APUs as well, and socketing them to allow customers to do upgrades or system replacement without having to desolder. So let's talk about some of the advantages of sockets. So from a design standpoint, it allows some flexibility. During the system design and development stage, sockets allow easy IC replacement and troubleshooting. So rather than having to desolder a chip from your board, you can do system level testing during the design phase of systems, rather than having to do, SMT the chip directly to the board. You can do system level testing without having to worry about the chip being permanently attached to the board. The socket can help you and your end customers ramp to production without a costly learning curve of directly attaching packages and chips in high temperature SMT reflow. Like I mentioned in the first bullet, you can do a lot of system level testing and debug without having to work with a direct attached chip. You can do a lot of your design with a replaceable chip. Okay. Assembly. Sockets let manufacturers standardize and simplify the assembly process. A single soldering process can be utilized regardless of package requirements. So oftentimes you can reflow all of your board side connectors on at the same time. Sometimes IC devices require specialized or customized SMT processes, which could lead to defects. You take that IC SMT out of the equation when you're socketing. During production initiations, new IC packages are often unavailable until HVM. With sockets, the assembly can proceed without interruptions. IC can be simply plugged in when they arrive. So the advantage of socketing something is that you can do your system level board design, system design quarters before the chip customer provides devices, rather than having to wait for that chip. And then once the chip arrives, you'll be able to simply just plug the chip in and then continue design and testing. And then final system configuration can be decided at the final assembly stage. So again, if something is designed for one particular generation and you decide to go to the next generation chip, you simply can just use the different chip rather than trying to change the socket. Supply chain management. This is actually one of the key ones here. In-process inventory can be limited since the IC could be plugged into the assembly. So essentially, from an inventory supply chain management, your chip can basically arrive when it's needed for final assembly of the system. The other key item is tariffs. Tariffs can be avoided by installing IC in the final system assembly in the country where the product is to be consumed. So as we know, if there are products produced in China or Vietnam, they can do system level BIOS boot testing, then with a golden sample, then remove that chip and ship the system without the processor or chip installed, saving on tariffs. Because as we know, sometimes when you put a chip inside of a system, the tariffs and fees become much, much greater. So once the final destination can install the chip directly by saving on cost. Okay. Avoiding direct component soldering. So increased package sizes, pin counts, reductions of solder ball sizes, all lead to yield loss during the surface mount SMT process. In addition, high assembly temperatures, which currently, again, in the SMT is around 260 degrees Celsius, and fast exposures to these highest temperatures can result in package damage in the form of delams, cracking, and popcorning. So when you decouple the SMT of a direct attach chip from your system, you don't have to worry about any of the solder joint problems that exist today when you are trying to reflow all of your components on at the same time. Okay, and you don't have to worry about customized temperatures. Okay. Reworkability. Sockets give you some advantages here from scrap replacement repair. Sockets eliminate the need to rework a BGA package from direct attach, so you don't have to worry about that. Socket rework or desoldering is a standardized process at OEMs and ODMs and has been for several decades to allow for PCB reuse. So there's a standardization if there is a defect or a problem with the socket due to damage or some other, it's easily desoldered and replaced with another socket, standardized today. Sockets allow for easy repair replacement of the IC device. If it becomes defective, ICs have a higher defect rate early in the product cycle, and often these are found at system level testing. So if you're an early adopter into the industry for a particular customer, and you get early samples of those ICs, and those ICs have some technical or defective issue, you don't have to worry about desoldering up from a board. You can simply just replace it with improved devices if they become better from that particular customer. The sockets, again, allow you and your customers to test and screen its product during production before a costly IC is assembled. So depends on, ODMs, they can do system level BIOS level testing to see if there's any issues before they get shipped to the end customer. Sockets, they allow you and your customers to replace a defective or damaged IC rather than reworking or scrapping the work in progress. So if there's a defective IC, you don't have to worry about reworking or scrapping the entire system level board. You simply just take the chip out and put another one in. Or if there's something else wrong with the board, another device on the board that has issues, you can save the IC and use it in another system or take it out while you're doing rework. The final bullet point here is it allows you and your customers to replace a defective or damaged module PCB without the loss of the IC. Like I mentioned in the previous slide, is there's another component on the board that has an issue or defect. You simply just take the chip out and reuse it on a different system or a repaired system. Okay. Each customer has their own unique pin assignments. Contacts are customized for each customer and application. There is no standardization and no one size fits all for a contact. Every contact that FIT has produced and will produce is unique to each application. There is no off the shelf, if you will, contact design. There are contact designs in our library, which we leverage to develop new contact designs for each customer design. Now, I've talked about LGA to BGA contacts and LGA to LGA dual compression. I'm going to highlight some of the key differences between the two. Your LGA to BGA, again, is your SMT type. And then your dual compression, there is no SMT. Size, LGA to BGA, there are some size limitations just because the larger the sockets get, the more challenges they become when it comes to warpage during reflow temperatures. Dual compression, there is no temperatures required, no SMT. And since the contact is so short and small and the housing is so thin, it will conform to the shape of the system during compression. So basically, it will flatten out to conform with the system shape. Like I mentioned earlier, warpage concerns, these LGA to BGA sockets have higher warpage concerns because you're dealing with larger bodies from injection molding, which tend to have higher warpage characteristics both at room temperature and at reflow temperature for dynamic warpage, whereas the dual compressions do not. Low profile, LGA to BGA sockets don't have as good as SI because you've got solder balls, which are typically around 0.5 millimeters, so that eats into your signal loss budget. And then also, sometimes the compression distance of the beam has to be longer based upon the customer requirements. If we look at the dual compression, it's got a very short signal path, so it's actually ideal for these higher speed signals as we get well above 56 gigahertz. Contact deflection, LGA to BGAs have better deflection if a customer so desires, whereas the dual compressions do not because of their shorter contact design length. PCB costs, BGA to LGA sockets have lower PCB costs just because you're not doing any gold plating. So you're basically just having a pad on the PCB, which lends itself to SMT. Dual compression have a higher PCB cost because you need to gold plate the PCB to have the interface between the contact tip and the PCB. SMT requirement, LGA to BGA, it requires SMT, which leads to higher energy costs at OEMs and ODMs. Again, energy uses in green environments is always a continuing and growing topic in the industry. Dual compression, there's no SMT. It's all done at room temperature in a clean factory room environment. So there's no SMT. Ease of handling, LGA to BGA, the industry has standardized its handling. It's less apt to any damage due to the protective cap. Dual compression have a little bit higher risk just because the bottom of the socket contacts are exposed during handling. But again, a lot of the OEMs and ODMs out there have standardized their process to mitigate those risks. So again, for every particular customer design guiding of sockets, if so interested, we can guide customers on what kind of socket they may need for their particular application. Okay.